Hello, my name is Brian. In this video, we will be covering the time-stepping algorithm utilized in all the Dynamics MATLAB projects. In this video, we're going to be covering physical inputs, initial conditions, basic numerical analysis, the history array, and generalized trapezoidal rule. In any MATLAB code, we always want to first start out with comments at the beginning of our code. This is going to explain exactly what our code does. Next, what we want to do is clear the command window and our workspace. So next, we want to define some physical problem data. This is data about the problem. So for instance, in this problem, we're going to have the acceleration due to gravity and the direction of gravity, as well as the mass of the particle. This is going to be information that doesn't depend on time. So this can be other vectors that you will need as well. Next, we want to define our initial conditions, just in like A2 when we're solving problems. The cool thing about this is we can change these values to explore the MATLAB code with different initial conditions. Now you must remember that these are chosen initial conditions. We can decide where the particle begins and at what velocity the particle will begin at. We can also decide what initial time we will use and what final time we will use. Next, we need to define some numerical analysis parameters that are appropriate for the given problem. In this case, we're going to need a time step, which is a dt. That's the amount of time that's going to pass between each step. And we're also going to need beta, which is used for generalized trapezoidal rule. Next, we're going to need to initialize our history array. MATLAB needs a way of storing information after each iteration of the time-stepping loop. So we need to store data in this history array. Most of the time, this code can remain exactly as it looks. You're only going to need to change the number of items that you're going to want to keep. That's going to be your x values, your v values, your a values, and any other things that you'll need. And the number of items that you report, you may also want to change. However, the rest of it can remain exactly how it is. Next, we're going to initialize our initial time, and we're also going to set out equal to 0 and I out equal to 0. This will be for deciding whether or not we want to keep something to the history array, since we don't actually need to keep each time step in the history array. Here, we're going to set our initial conditions to be our xold and vold values. That's going to initialize our time-stepping algorithm. The last thing we need to do before starting the time-stepping algorithm is to initialize our acceleration. The important thing to remember here is that this is a calculated acceleration. You're not going to decide some random acceleration here. And the cool thing about this is we can use our old acceleration to integrate for our velocity, and then we can use that velocity to integrate with our position. That's going to be where generalized trapezoidal rule will come in. So now we're going to start our time-stepping algorithm. We're going to use a big for loop, and we're going to iterate over each time step. So the first thing that we want to do is write our information to our history array. So we're going to have an if statement because we don't need to store every single value inside of our history array. If out equals 0, then we're going to be storing. And this gives us a little bit less information that we have to deal with. And the history array is going to look exactly like this, and we can add in values. So we can put t, xold, and we're going to transpose it, and then vold and transpose that. And we can also store more information as the problems get more complex, like energy and other information. Next, we're going to increase the time step by dt. This is kind of confusing notation if you're not familiar with it, but what you might be familiar with is that t new is going to be equal to t old plus some dt. So we're updating our t value to equal our t old, and then we're going to increase it. And then we can compute the new acceleration from our equation of motion. For nonlinear problems, you must solve the new acceleration by Newton's method, This problem doesn't need this since it's a linear problem. However, with nonlinear problems, you're going to need to include Newton's method here. Next, we can implement generalized trapezoidal rule. This is going to be a piece of code that never needs to change because we're always going to need to integrate with respect to time. We calculate v nu using a nu. This is a numerical analysis, and then we calculate x nu using v nu. Finally, we update our a old, v old, and x old with the new values we just calculated in preparation for the next time step. And then we're going to repeat that over and over and over, and that's the end of our for loop. This is the end of the essential parts of the time-stepping algorithm. More is going to be needed when you're analyzing nonlinear systems. As I said, you're going to need to implement Newton's method. You're also going to need to implement plotting commands, as well as printing to the command window to make it usable. But this is the essential part of the time-stepping algorithm without all of the stuff that can be kind of confusing.